For this tutorial video, we're going to understand the application of electromagnetic induction in a dynamo. So there are two types of dynamo. The first one, the direct current dynamo, and the second one, alternating current dynamo. So today we will first learn the direct current dynamo. So first of all, you may take a look at the structure of a direct current dynamo. So it's pretty similar to a direct current motor. The only difference you can see is the wire is connected to a battery, not connected to a battery, but connected to a load. So this load could be probably a resistor or a bulb. So, and another thing, in a motor we provide current in order to make the coil rotate. So this coil, for motor, we provide a battery so that it has current flowing and then the coil will rotate. But for dynamo, there are no batteries. So we rotate this coil in order to produce current in the circuit. Now let's take a look at the operating principle of a direct current motor. So I label the left side of the coil, this side of the coil, as A. So I'm going to do this for each of this, A, B. So this is the axis of rotation, just like this. So this is the commutator, this is the coil, exactly the same. So this is a pair of commutators with carbon brushes and with a load. And for the coil part, you have a north pole and a south pole of permanent magnet. So it means that the magnetic field is in this direction, always in this direction, from north to south. Okay, so now we assume that this coil, we rotate it in a clockwise rotation. So if it's a clockwise, the A side will be moving upwards, the motion will be upward. So for the B side, the motion will be downward. So this is the motion, this is the motion. So next thing, we can see that this motion, the upward and downward motion, is perpendicular to the magnetic field, the B force. So in this case, we have to apply the Fleming's right-hand rule. Remember, this is a dynamo, so we have to use the Fleming's right-hand rule instead of Fleming's left-hand rule. So applying the Fleming's right-hand rule, FBI, the B is in this direction. So for the A side, the motion, the force, the motion or the force is in this direction. So you can see that B, this direction, M, this direction. So the current, we call it the induced current, is in this direction. So means that there will be current flowing in the coil. Now we move on to the part B, the side B. So same thing, B force in this direction. The M, the force, the motion is in this direction, moving downwards. So the induced current is in this direction. The current is induced in the coil. So this is how the current flow. So we put it back here on the commutator part, flow like this. So we continue from here and then back here. So this load will be pointing at this direction because the current is flowing towards the left. Next, we rotate it 90 degrees. Oh, before this, let's take a look at the graph. So at this point, you can see that the motion, the force, is 90 degrees to the B force, the magnetic field. So at this position, the induced current will be maximum. So at 90 degrees, it will be maximum. So this is number 1. So this is where, assuming this is current maximum. So this will be the position of part 1. Next, we move on to part 2, where we rotate the coil for another 90 degrees. So the coil will be looking like this. This is the axis of rotation. So after we rotated it 90 degrees, so this will be A, this will be B. Now, the motion, as we stated just now, will be a clockwise rotation. So the motion here will be towards the right, motion here will be towards the left. Okay, now you can see that the motion, the direction of motion, the force, is parallel to the B field. So since it is parallel, you cannot apply the Fleming's right-hand rule. So it means that if it's parallel, there will be no induced current in the coil. So in this case, the induced current will be 0. So back to the graph. The position of part 2 will be here, because the induced current will be 0. Next, we move on to part 3. Again, the axis of rotation. We rotate the coil once again, another 90 degrees. So A will be here and B will be here. Now, clockwise rotation means that here is moving downwards, here is moving upwards. So let's take a look whether the motion, the force, is perpendicular to the magnetic field. So this is upward, this is towards the right. The B field is towards the right. So it is perpendicular. So means that there will be induced current because we can apply the Fleming's right-hand rule. So let's do it on part B. The motion pointing upwards, B field is towards the right. So the induced current will be like this. Again, we do it for part A. M here, B here. So the induced current will be in this direction. So since it is perpendicular 90 degrees to the magnetic field, so the current will be at maximum. So same for part A, it will be at maximum. So what is the direction of flow of the current? So it will be in this, just like part 1. So back to the graph. Again, rotated it 90 degrees, so it will be at maximum. So this is part 3. You can see that it's at maximum. So this is part 1, part 2, part 3. So back to the diagram. After we rotate it again clockwise, so the axis of rotation, B will be up here, A will be down here. So again, clockwise rotation means that it's in this direction for B and it's in this direction for A. So you can see that for both sides, the direction of motion are parallel to the magnetic field. So we mentioned it quite a lot of time just now, as if it's parallel to the magnetic field, there will be no induced current. So as you can see, for the Fleming's right-hand rule, all 3 components, they are perpendicular to each other. The F is perpendicular to the I. The F is perpendicular to B. The B is perpendicular to I. So it must be perpendicular to each other. So in this case, there will be no induced current. So there will be no current flow in the wire. So back to the graph. Part 4 will be 0. So as it rotates, the value of the induced current will decrease. So we should plot the graph like this. A curve upwards and then reach the maximum and then back to minimum. And then a curve outwards again, reach the maximum and then back to minimum again. So this is how the graph of the output of a direct current dynamo looks like. So in the next lesson, we'll be learning alternating current dynamo. So stay tuned and thank you for watching. Goodbye.